Hello, and welcome back to the course on Physics for Engineers. So we are still on the 11th chapter for this course. So before we proceed with this lesson, let us first review some concepts. So in the previous lesson, we have discussed about the relationship between the electric charge, electric field, and electric force. And they are all related by this equation. So if you have a positive charge, the direction of the force due to acting on Q, due to an external electric field, take note that this electric field is not the electric field of Q, but external, is in the same direction. But if you have a negative charge, the direction of the force is in the opposite direction. So for this lesson, we will now be trying to calculate explicitly the electric field and the electric force of a point charge using Coulombs law. So Coulombs law is mainly for calculating the electric field and electric force for a discrete charge distribution. So if you have a discrete charge distribution, this means that you can count, or you can actually see each of the charges. So it's discrete. So if you want to calculate the magnitude of the electric field, then it's given by this equation. This is the electric field of a point charge. So this is the Coulombs law for electric field. So K is just some constant. We have the absolute value of Q over R is the distance from the point charge to the point where you want to find the electric field. So that point is what we call the field point. So the direction of the electric field, of course, is always along the line connecting the source point charge and the field point. And it depends on whether it's positive or negative, but it's along that line. So similar with what we have discussed in the previous lesson. So for example, if I'm gonna try to find the electric field direction or the electric field at that point, then what will I do? What I will do is use this for the magnitude, and for the direction, I just connect the two. And since this is a positive charge, then the direction is away from the charge. So, but it's always along the line connecting the charge and your field point. So K is just a constant, which is equal to 1 over 4 pi epsilon naught, and epsilon naught being the permittivity of free space. But K is just equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. So for the force, this is now the Coulombs law for a force. This is now the force between 2 point charges. So if you want to know the force between a force exerted by Q1 and Q2, or Q2 and Q1, then their magnitudes are actually the same, but their directions are opposites. Just I have explained in the previous video here. But this is the magnitude of the force. It's K, absolute value. Take note of the absolute value because this is magnitude, this is positive. Absolute value of Q1, Q2 over R squared, where R is the distance between Q1 and Q2. So the direction of the force again is along the line connecting the two charges. So for instance, the direction of the force exerted by this Q on this negative charge here is in that direction, but it's along the line connecting them. But if you want to take the direction of the force exerted by the negative charge on the positive charge, it's still along this line, but it's in the opposite direction. So if for instance this is Q1 and say this is Q2, then this force here, this force is the force exerted by Q1 on Q2, F12, and the force exerted by Q2 on Q1 is in the opposite direction, but they will still have the same magnitude. So this is F21, the force exerted by Q2 on Q1. So he will pull, or the Q2 will pull Q1 towards itself, which they want to attract. So they're pulling actually each other towards themselves, hence you have an attraction. Okay. So let's now go directly to an example. So in our first example, this is an example of Newton's third law of motion. So the force between two charges. So we have two charges, Q1 and Q2. Q1, they are both lying on the x-axis. Q1 is at x is equal to -2 meters. Q2 is at x is equal to 1 meter. The Q1 is 1 nanocoulomb. Nano means times 10 to the -9. Q2 is 2 nanocoulomb. So again, it's 10 to the -9. So we are asked to find the force exerted by Q1 on Q2 and the force exerted by Q2 on Q1. Okay, the force exerted by Q1 on Q2, the force exerted by this guy or this charge on this charge will be, since this is positive, then Q1 will repel this charge away in that direction. So this is the force exerted by Q1 and Q2. So it's along the positive x-axis. But how about the reverse? What's the force exerted by Q2 on Q1? So since Q1 is positive and Q2 is also positive, then Q2 will push Q1 away from itself. So it will push, Q2 will push Q1 in that direction. So this is F21. So for letter A, we already know the direction. So we only need to find the force, the magnitude of the force. So F12 magnitude is just K, absolute value of Q1, Q2 over R12 squared. So I just place a subscript R12 to signify that this is the distance between Q1 and Q2. Because in the future, there will be more charges. So you will need to have a subscript in your distances. Okay. So this is the force exerted by Q1 and Q2, the magnitude of the force exerted by Q1 and Q2. So K is just a constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. Absolute value of Q1. Q1 is 1 nanocoulomb, so that's 1 times 10 to the -9 Coulomb. Q2 is 2 nanocoulomb, so you have 2 times 10 to the -9 Coulomb over their distance. What are their distance? So Q1 is at x is equal to 2 meters. Q2 is at x is equal to 1 meter. Then their distance is 3 meters. So you have 3 meters squared. Of course, the final unit of that should be Newton because this is a force. And you will get a value of 2 nanonewton or 2 times 10 to the -9 Newton or 2 nanonewton. That is the magnitude. And since we already know its direction of F12 is towards the positive x-axis, then the F12 vector is just equal to 2 times 10 to the -9 Newton positive I hat. That one. Now, for letter B, it's the force exerted by Q2 on Q1. So we already know its direction. It's towards the negative x-axis. So we try to find its magnitude. So this is Q2 Q1 over R21 squared. But you will still, substituting all these values, you will still get the same result. 2 times 10 to the -9 Newton. That's the magnitude. Its direction is actually negative I hat. So therefore, F21 is equal to -2 times 10 to the -9 Newton I hat. 2 times 10 to the -9 Newton negative I. That one. So you will notice that they have the same magnitude, but the directions of the force exerted on each other are different. So the magnitude, they have the same magnitude, 2 times 10 to the -19. The direction of F12, this force, if you're asked for the angle, it's 0 degrees or towards the positive x-axis. For F21, force exerted by Q2 on Q1, it's negative I hat, or in terms of theta, that is 180 degrees. And these are the forces, and this is Newton's third law of motion. The force exerted by Q1 and Q2 is just the negative of the force exerted by Q2 on Q1. So, law of action and reaction. For every action, there's always an equal in magnitude, but an opposite reaction, opposite in direction. Next example, vector addition of forces. So what is the magnitude and direction of the total force on Q3? So the total force on Q3 will be due to its neighbors. So its neighbors are Q1, 1 nanocoulomb, located at x is equal to -1 meters, and Q2, -1 nanocoulomb, located at y is equal to -1 meter. So Q3 is a negative charge, and it is at the origin. Okay, so the total force on Q3 will be a superposition of the force exerted by Q1 on Q3 plus the force exerted by Q2 on Q3. Now, let's try first finding the directions. So F13, the direction of the force exerted by Q1 and Q3 will be in this direction towards itself because it's attraction. And Q2 is negative, Q3 is negative, then there will be repulsion between these two. So Q2 will push Q3 away from itself. That is F23. So we already know the direction. Therefore, if you use a parallelogram method in adding these two vectors, we expect that our force, the total force, will be in quadrant number 2. So that is the total force. Okay. So we already know the direction. F13 is actually, it has a magnitude of F13, and the direction of F13 is obviously in the negative I hat. And then F23 has a magnitude of F23, and its direction is positive J hat. So in order to solve this problem, we only need to solve their magnitudes. So use Coulombs Law. So F for the magnitude, so F13 is just K, absolute value of Q1, Q3 over R13 squared. So Q1 and Q3 are given, their magnitudes are given. R13 is the distance between Q1 and Q3, and in this case, it's obviously 1 meter because x is at Q1 is at x is equal to -1 meter. You will get a value of 9 nanonewtons, or 9 times 10 to -9 newtons. So for F23, still do the same. So absolute value of Q2, Q3 over R23 squared, you will still get the same value, 9 times 10 to -9 Newton. So you substitute this to that, and you can now find your total force vector. So your total force vector on Q3, the total force exerted in Q3 will be, substitute this on that, you will get -9 times 10 to the 9 Newton I hat plus 9 times 10 to the 9 Newton J hat. So it has a negative x component, it's a positive x component, sorry, y component, therefore it is in quadrant number 2 as we have predicted. So it's in quadrant number 2. So if you take the magnitude of that, you just use Pythagorean theorem. So square root of the x component squared plus the y component squared, and you will get a value of 1.27 times 10 to the -8 Newton. So just use the Pythagorean theorem. So square root of the x component plus the y component squared. And to get the angle of this vector, so theta 3 is this angle here. It's just tangent inverse of the y component over the x component. And in this case, this will give you a value of 135 degrees. So again, always make sure that the angle that you get corresponds to the quadrant where the vector is located. So that is the magnitude and direction of the total force on Q3. Okay. This is now vector addition of electric fields example. So this is actually a similar problem, but we take Q3 out of the picture. And we are just after the total electric field at the origin. Okay. So in order to find the total electric field at the origin, it's just a superposition. The total electric field is just a superposition of the electric field due to Q1 at the origin plus the electric field due to Q2 at the origin. So the electric field due to Q1 at the origin will be that direction. Again, the direction is always along the line connecting the point charge and your field point. And in this case, since it is a positive charge, so it's pointing away from the charge. For the negative charge, again, it should be along this line. And since that is negative, so it's pointing towards the negative charge. That is E2. So by adding using parallelogram method, you will expect that the total force or total electric field, sorry, will be in quadrant number 4. So quadrant number 4. Okay. Sorry. So you do the same. So we know that E1 has a magnitude of E1. Its direction of E1 is I hat. E2 has a magnitude of E2. Its direction is negative J hat. So to solve this problem, to find the total electric field vector, we just need to find the magnitudes E1 and E2. And we do that by using Coulombs Law. So E1 is just K Q1 over R1 squared. Where R1 again is the distance between Q1 and the field point, the point where you want to find the electric field. So it's the origin. That is obviously 1 meter. And you will get a value of 9 Newton per Coulomb. So you do the same for E2. It's just K Q2 over R2 squared. R2 again is the distance between Q2 and the point where you want to find the electric field, which is obviously also 1 meter. And you will also get a value of 9 Newton per Coulomb. So therefore, your electric field vector now will be E1 is 9 Newton per Coulomb, so 9 Newton per Coulomb I hat. And then E2 is also 9 Newton per Coulomb, but there's a negative sign here, so minus 9 Newton per Coulomb J hat. So positive X component, negative Y component, so that corresponds to a vector in quadrant number 4. So positive X, negative Y. So quadrant number 4. So to get its magnitude, Pythagorean theorem, square root of the X component squared plus the Y component squared. And you will get a value of 12.7 Newton per Coulomb. And to get the direction, so this is our total electric field vector. This is the vector. And to get the direction is this one. So measure from the positive x-axis counterclockwise. That is our direction, theta. So to get the theta, tangent inverse of the y component over the x component. And your calculator will actually give a negative value. So the value given by your calculator is actually this one. So a negative angle means you measure from the positive x-axis clockwise. So if the instruction explicitly states that you measure the direction from the positive x-axis counterclockwise, then you have to add the answer given by your calculator, because your calculator will only give this angle, which is a negative angle because this is clockwise. So your calculator will actually give you an angle of 45 degrees, negative 45 degrees, and you need to add 360 to that so that you will get this angle, which is 315 degrees. Okay, let's place an additional problem. What if we place Q3 back in the origin? What if we place Q3 there at the origin? What is now the magnitude and direction of the total force on a charge Q3 placed at the origin? So this is the same problem as in the previous example exactly. But since you have already solved for the total electric field, you must take advantage of that. So knowing the total electric field in this direction, and since this is a negative charge, so meaning this will move, or the force will be in the opposite direction, because negative charges always move opposite the direction of the force. And this is actually what we got in the previous example. F3 is in quadrant number 2. So this is the relationship to the two vectors, the vector electric field and the vector electric force, Q3. And their magnitude is also related, but you just have to take the absolute value of Q3. So F3 is just absolute value of Q3 times the absolute value or the magnitude of the total electric field, which is 12.7 Newton per Coulomb. And you will get exactly the same answer. 1.27 times 10 to negative 8 Newton. And since the direction is opposite, what is opposite of 315 degrees? So it's either you add by 180 or you subtract by 180 to get 135 degrees. So this is exactly what we have obtained in the previous example. So now, as you can see, there are two ways to solve for force. You can use the Coulombs law for force, or you can find the total electric field first and then multiply it by Q to find the total electric force. So there are two ways to solve for electric force. By solving it directly using the Coulombs law for electric force, or by solving the electric field first and then multiplying by the charge at that point. Okay. So that ends this lesson. So in the next lesson, we will still try to calculate the electric field, but now for a continuous charge distribution. So what if you can no longer see the individual charges in a distribution and they are now continuous? So when you say continuous, what if the charges now form a line? What if the charges now form a surface? Or what if the charges now form a volume? Then you can still use Coulombs law, but it will be very hard. It will be very tedious. So in that case, we will use an alternative method. And that method is called Gauss law. So we'll discuss that in the next lesson. So I will see you again by then.